Okay, we're going to go through the last part of chapter 17, talking about diprotic and polyprotic acids. So di meaning two, poly meaning many, so two or more. What we call an acid that only has one proton, it would be monoprotic, would be one H plus. So protic meaning H plus. So acids that give off more than one hydrogen ion. So for example, carbonic acid is diprotic because it has two hydrogens. It gives off one proton at a time. We call this deprotonation, giving off a proton. You also can think about it as ionizations, dissociations. There's a few different words we can use here. So the first hydrogen comes off, giving us bicarbonate or hydrogen carbonate. We have our Ka. We're going to call this Ka1 because there's another Ka because there's another H to come off. So we have products of our reactants here. This is excluding the water, so it's got hydrogen instead of hydronium. Then we have the bicarbonate, carbonic acid, the bicarbonate, which is the conjugate base of carbonic acid. But it is also amphoteric. It can act as an acid or a base. So if it acts as an acid, gives off H, makes carbonate, and then we get Ka2. Now this is, again, not including the H3O plus. The reason why we would write it like this is just to save a little time. And we're like, hey, we know that actually there's water there, and we know that's really H3O plus, but this is just to save some time. So you may see people do this. The first Ka is always greater than the second Ka because it is easier to get rid of an H in this case versus this one, because this ion is negative. So it's harder to get rid of that H plus. So each successive acid is weaker because the Ka is smaller. So here are some Kas for different diprotic, polyprotic acids. We can see how they get smaller as they go. So look at this one, phosphoric acid is 3, so it gets smaller and smaller as you go. We have 3 H's that we can remove. So how would we use this? Oxalic acid is a poisonous substance used mainly as a bleaching agent. Calculate the concentrations of all species present in equilibrium in a 0.1 molar solution at 25 degrees C. I wouldn't say that you needed to be able to do a question like this on a test. I think that you would probably need to be able to write all of the equilibrium like expressions and the reactions for each deprotonation or each ionization of oxalic acid, but I don't think that you would have to do all the math, but I'll show you what that looks like. So why don't you just try to write the reactions and the K expressions and maybe get started on that first reaction ice table. Okay, so my first reaction is going to be H2C2 H2C2O4 aqueous plus H2O liquid. And then we're going to get rid of one of those H's. So we're going to keep one H. We're going to get rid of one of those H's. Oh, you need the Ka values. So the Ka values are actually in this chart here. First one, so this would be my Ka1. So we can say Ka1 is equal to 5 times 10 to the negative 2. And then we can say Ka2, the second one, was equal to 1.6 times 10 to the negative 5. We're just getting that from the chart from the previous page. I'm going to leave some space here because I'm going to show you how we can calculate this. So then we take the second one, C2O4 minus, react it with our water, and we make C2O4 2 minus and another hydronium. This is Ka2. Now if I put in 0.1 molar in this first one, I'm putting the R there because I know some people were having trouble figuring out the difference in the reaction and the initial amounts. So just to differentiate that for you. Having a hard time with straight lines. So if I start with 0.10 molar of my initial solution, I would start with 0 here. We would have minus x plus x plus x. So we would have 0.1 minus x, probably doing x as small. Then what would be our initial for the next one? So for the next one, it would be whatever our equilibrium was of that ion would be the initial for the next one. I don't know if you've picked up on this quite yet, but I'll draw it out for you. This would be the amount we start with here. So I'll just say x. We would have 0, 0 for this new one. At the end, we would add up here and here. Well, I guess we could get a total. So you could technically, let's see, what did they do in the textbook? They go with x. Okay, so this is x here, and it comes from this being the hydronium here. We still have to go to the right. So I'm just gonna say y. So what are our equilibrium concentrations of everything? Well, at equilibrium, we would have however much of this is in equilibrium. So my final answers would be however much of this, and then whatever x minus y is for this one, and then whatever y is for this one, and then whatever x plus y is for our hydronium. So what I've got in pink are all of my final equilibrium concentrations. So final concentrations in pink. And we would have to do 2 ice tables. Like you'd have to do, to solve for x for this one, you got to use Ka1, and then to plug these x's in, and then we solve for y's for this one using Ka2. You can see how we would work that out. If you want to give it a try, the answers and the work are all listed out here. They cut out the water, so they don't have hydronium, but they do have just hydrogen ion. So see how it kind of cuts you some time to leave the water out. And then they kind of set this up the same way here. And then they work it out. So you can check. They do have to solve quadratic for that first one because x is not actually small. So again, I wouldn't be worried about trying to solve quadratic on the test. Just use a quadratic formula calculator. If you wanted to practice the algebra, you can. Don't take too long with it though. You may have to set up the quadratic on the test. Like you may have to get to the point where you can rearrange it to get this. So I don't think we'd ask you to actually calculate it. The next topic is the acid-base properties of salt solutions. So salts are ionic compounds that we get from acid-base reactions, but you can kind of think about them as ionic compounds because there are many of them that can be made. So ions produced by the dissociation of salt with water either makes hydroxide or hydronium. And so we call this hydrolysis, meaning the separation or reaction with water. Conjugates of weak acids are basic because what's the conjugate of a weak acid? It's a conjugate base. So for example, if we have HF plus water, do you see how F gets to go backwards? F gets to be a base. So if we let F minus or a fluoride be a base, what does it make? Here we go. So we can write the actual reaction of the conjugate base as a base. And this means that if we see F minus, we see that anion in a salt, like sodium fluoride, for example, that salt would have a basic pH because the fluoride is going to act as a base because it can go backwards because it's the conjugate of a weak acid. If you have conjugates of weak bases, so for example, if I have ammonia and water, I make ammonium and hydroxide. But look, the ammonium gets to go in reverse. So it gets to act as an acid. So let it act as an acid. What does it make? It is an acidic salt because if we have ammonium chloride, for example, then the ammonium would act as an acid. So that salt in water would be acidic. So not all just like ionic compounds in water are going to be neutral. Some of them will. And then I'll add that here. So cations of strong bases and anions of strong acids are neutral ions. So because they don't get to go backwards, they only go one way because they're the byproducts of strong stuff. So here's a nice little chart for you. I'm going to just skip this for a second and show you the chart. Here's a chart. I don't want you to worry about this row. Basically just conjugate acids of weak bases, conjugate bases of weak acids, and then basically this is all strong stuff. Products of strong acid base dissociations. So when you break apart a strong acid or base, whatever you get is neutral because it can't go back and be an acid or base. So here is again, don't worry about this one. It's true, but we don't need to worry about this on a test. Here's an example to work out your ice tables again. What's the pH of a 0.1 molar solution of sodium hypochlorite? Ka for hypochlorous acid is 4 times 10 to the negative 8. So why don't you give that a try? Just write it out first. So sodium hypochlorite and HOCl. So let's write out HOCl plus water makes OCl minus plus hydronium. Do you see how NaOCl makes sodium and hypochlorite? So this is the conjugate of a weak acid, which means it's going to be the conjugate base, which means this is a basic salt. And the sodium is neutral, so it's not going to affect the pH because it comes from a strong base. So let's let this hypochlorite be basic. If it's basic, it's going to react with water, and it is going to accept an H and steal that H from the water. Now, what would the K be for this? If the Ka for the acid is 4 times 10 to the negative 8, what would be the Kb of the hypochlorite? It would be Kw divided by Ka. So my Kb would be 1 times 10 to the negative 14 over 4 times 10 to the negative 8. So the K for this reaction is not just the Ka, so you got to be careful because if you're not doing an acid reaction, you can't use Ka. So if you're using the conjugate base of that acid, you got to figure out what the Kb is. So we get 2.5 times 10 to the negative 7. So now why don't you try working out the ice table, and we're trying to figure out pH. So think about what in this reaction can help us find pH. So hopefully you've tried it. So we have our reaction. Table really quick. Again, I always draw my lines right under the plus signs and right under the arrows. Water is a liquid, so we don't have to worry about it. They give us 0.10 molar hypochlorite solution. And I got to make sure that we're using mole ratios here because it's a 1-to-1 ratio. We can just use this number. But what if it was a magnesium hypochlorite or something, right? Then we would have to worry about it being 2, or calcium hypochlorite. So just make sure you're paying attention to those little details. We start with 0 of our products, so it means we must be moving towards the right because we cannot subtract from 0 when we're talking about matter. Again, we always just make sure we're looking for those coefficients, but they are all ones. And then I plus C equals E. And then we have our Kb. Let's write the Kb expression. It's going to be my my products over my reactants. And again, we exclude the water. And then I can plug in. And of course, we have the opportunity here to we always want to try to not do quadratic. Do you see how my K is very small? Let's try X is small. So we'd be multiplying both sides by 0.10. So you're going to get 2.5 times 10 to the negative 8. And then we would square root both sides. We would get 1.6 times 10 to the negative 4 as my X. And that is equal to the concentration of hydroxide. Did you figure out that it was the concentration of hydroxide that we really need to get in order to find pH? And we can do this in a couple different ways. But maybe you're thinking, hey, I know I can get POH from this. So why don't we get POH, and then we can get pH from our POH. You could also do your KW is equal to hydronium times hydroxide. And we can plug in the hydroxide and get hydronium, and then we can take the pH from there. So kind of decide what we want to do, and then from there you can work. So I'm just going to give you, so for this one, then you would do, so then we would do 14 is equal to pH plus POH. So that would be my progression to find what I'm looking for. If I did this one, then it would be pH is equal to negative log of hydronium. And you can see how I'm kind of highlighting the similarities and how we would work this out. So at the end of the day, I want you to try to work it out and see what you get. Just pick a method. I get 10.20 for my pH, which makes sense that it's basic. It should be basic because we know that hypochlorite is a conjugate base of a weak acid. So the salt, including hypochlorite, would be basic. So you can always check your work with your understanding. Here's another example. Why don't you try this one? And then if you have questions, the solutions are after this. All right. And then you might also have not just a full-on ice table, but just a quick, like, is it acidic, neutral, or basic? Let's do some of these. So I want you to go ahead and pause and try this one. I don't want you to do any math. I want you just to predict, is it basic, acidic, or neutral? And then we'll take a look at it. So for A, you have lithium iodide. Let's break it into two pieces, lithium ions and iodide ions. Where does lithium come from? Lithium looks like lithium hydroxide, right? That's a strong base. Where does iodide come from? It looks like it comes from HI, which is a strong acid. So if you have a strong base, strong acid combination, your conjugates don't actually get to do anything. So we would call this neutral. For B, we have ammonium nitrate. We need to split this in two. So we have ammonium ions and nitrate ions. Ammonium comes from ammonia, which is a weak base, which means this would be a conjugate acid. Nitrate comes from nitric acid, which is a strong acid. So we have a conjugate acid, which means our salt is acidic. I don't want you to worry about, oh no, this one we can do. This one we can do. Just the other two. So strontium nitrate. So strontium comes from strontium hydroxide, which is a strong base. And then we have nitrate comes from nitric acid, which again is a strong acid. So we have neutral. Next one, we have KNO2, K plus. This comes from KOH, which is a strong base. NO2 minus is nitrite, comes from nitrous acid, which is a weak acid, which means this is a conjugate base. So this one will be basic. Then we have NaCN. So sodium comes from sodium hydroxide, which is a strong base. So no pH changing properties there. And cyanide comes from hydrocyanic acid, which is a weak acid. We know that because it's not strong, so this means it's a conjugate base, which means it is basic. That's how you would go about solving without doing the whole ice table and pH calculations. You definitely have to do this on the test, so make sure that you know how to do this. The textbook has their explanation there. If you have a salt where you have both the cation and the anion that do stuff, you would have to kind of tell if the Ka, which one is greater. However, I don't want you to focus on this too much for the test. You may see it in the homework, but we don't need to worry about it on the test. It'll be like this, where there's like clear, one is neutral or both are neutral. Then the last topic for this chapter is Lewis acids and bases. This is just a very brief topic. You're going to see this more in organic chemistry, but this is a secondary type of definition of acids and bases, with not talking about hydrogen changing, but talking about electrons changing. So Lewis bases donate electrons. So now the bases are doing the donating, and the acids accept a pair of electrons. So we've already actually been doing this because you've seen how bases use their electrons to go grab that H, right? They donate that extra pair. And so if we see a bond forming, I'll try to color code this for you. Excuse me. So if we see these blue electrons are now this bond, do you see how the ammonia, the N, donated its lone pair? It doesn't have a lone pair anymore. It donated its lone pair to make this bond. And how the boron did not have any electrons on it, and now it has extra electrons on it, so it accepted the bond, which is accepting those electrons. So Lewis acid here is accepting and a Lewis base here is donating, but it's electrons, not hydrogen ions that we're accepting and donating. So just draw Lewis structures and just see who gave up their lone pair and who accepted a bond. And so you can practice here, just thinking about who is giving up a lone pair, who is accepting. These are a little bit difficult, but I think you can probably try to figure it out. If you're not sure about like what Lewis structures look like, I can give you some help with this. So for A, you would have C, C, O, C, C, and then we would have H's like this. On the test, if you had to draw Lewis structures for this, it would be a lot simpler. Now we would have Al. Now AlCl3 is a weird one. Aluminum is actually acting covalently here. And you can see we're literally just putting them together. So even if you don't know what the Lewis structure looks like, can you think about who would be donating? So basically we have this weird looking guy. So if you can tell who is donating and who is accepting electrons, who is accepting a bond and who gave away a bond or gave away an electron pair. And so why don't you try the same thing with B? Just draw it out, see what you get. The answers are in the next slide. All right, that's all for chapter 17 and almost all for our test. We have one more little tiny bit in chapter 18, but not to worry too much about it. And then we will have our exam.